Hello, I'm Lucas Young, and this is the feature-aligned network with knowledge distillation for efficient denoising. Image acquisition is inevitably contaminated by noise due to various environmental effects, such as low light. This noise is especially severe in images captured by small devices such as smartphones and wearables. These smartphones and wearables often have greatly limited compute. Hence, an efficient image denoising algorithm is highly desirable to denoise the severe noise while also being efficient enough to be practically deployed on these compute-limited devices. Our method achieves visually comparable results to the state-of-the-art Cycle ISP while having 263 times fewer max. Our work is distinguished by three main contributions: the feature-aligned layer that modulates the activations of an encoder-decoder architecture with the input noisy images, a novel feature matching loss that allows knowledge distillation from large denoising networks in the form of a perceptual content loss, and an empirical analysis of our efficient model trained to specialize on different noise subranges. Our efficient UNet architecture is optimized to be small enough to be deployed on a mobile device, and is distinguished by the ARNet block, the shrink skip connection, and the feature aligned layer. The ARNet block is a variant of the MobileNet v2 block, in which we replace the depthwise convolution with a group convolution, which allows more efficient memory access. In these memory-constrained devices, the skip connections are quite expensive because they store features from the encoding to the decoding. And the maximum memory activation is important because if the maximum memory activation is too high, that will cause a DRAM spill, in which a DRAM access is more expensive than SRAM access. So to limit the maximum memory activation of our network's forward pass, we shrink these skip connections with a point-wise convolution. We propose the feature-aligned layer of our network. So as shown in our experiments, efficient denoising networks are very prone to washing away original input detail present in the input image during the processing with its stack of multi-scale convolution and nonlinearity layers. So inspired by the SPADE architecture, we propose the feature-aligned layer, which integrates the input noisy information at each layer of our network. So specifically, at each ARNet block pass, we apply convolution to the scaled original input image, and this convolution predicts a scale and a bias that is then applied to the output of the ARNet block. So put together, our UNet now looks like this, in which the skip connections are shrinked, the blocks are replaced with ARNet blocks, and the feature aligned layer is applied after every ARNet block, reintroducing the original input details. To evaluate the performance of the feature-aligned layer, we compare it to a plain UNet and a plain UNet that does not have the feature-aligned layer, but does have a wavelet transform applied. You can see that the metrics are very similar, but the visual results reveal that the feature-aligned layer has slightly better detail. And this also reveals that the traditional PSNR and SSIM metrics may not capture the high-frequency details. We also see that the feature-aligned layer without the skip connections has worse performance than the feature-aligned layer with skip connections. And this shows that although the feature-aligned layer has a similar purpose to skip connections, reintroducing the original input details, they are not redundant. Further visual results show the benefit of the feature-aligned layer as opposed to the wavelet transform model. The model with the feature-aligned layer has much better detail in the high-frequency domain. So these traditional PSNR and SSIM metrics don't fully capture the benefit of the feature-aligned layer. One capability that's often missing in these efficient denoising networks is the capability to encode image features at a higher and more perceptual level that large denoising networks can do. These large denoising networks can make imaginative judgments that can fill in the blank of missing textures. So we desire to transfer this capability to an efficient network, and so we propose the feature matching loss, which is aimed at knowledge distillation. So to perform the feature matching loss, we first train a large teacher denoising network, and this network happens to be 72 gigamax per megapixel. And then when we're training our efficient student denoising network, which is 2.7 gigamax per megapixel, we use the feature matching loss. And this loss is defined as the difference in content and style between the teacher network's activations on the efficient network's predicted image and the teacher network's activations on the ground truth image. And we find that using a loss like this that combines elements of a perceptual loss with knowledge distillation is able to transfer the knowledge that large networks have to the efficient network. We perform an ablation study on the loss function, which includes the Charbonnier loss. The Charbonnier loss is supposed to stand in as a baseline for any non-perceptual loss. We include the RGB perceptual loss, which is simply the LPIPS loss applied to the RGB image after post-processing our raw model outputs. And we also include a simple knowledge distillation implementation, which is simply defined as the loss is the difference between the teacher network's predicted image and the student network's predicted image. And finally, our feature matching loss. And so our feature matching loss has the best results when evaluated with a perceptual metric, that being LPIPS, applied to the RGB image. And we also confirmed this visually, that the feature matching loss has the most detailed visual results. Now we will briefly discuss the nature of image noise. Our method operates in the raw domain, which means that our method operates prior to the image signal processing. And image noise in the raw domain is Gaussian and not spatially correlated, meaning that there are no spatial patterns that can be observed in the raw image. The per pixel variance of these Gaussian distributions are linearly dependent on the signal of the pixel of the exposure, which we can see experimentally when we plot the variance of pixels versus their intensity on an image of a color checker. The slope of the relationship between signal and variance is also dependent on the gain, or ISO, of the exposure. As we can see here, a linear regression perfectly describes this relationship between gain and the slope of signal and variance. This gives rise to the problem of a wide problem space with very few parameters for an efficient network. So it cannot our efficient network cannot respond optimally to both minimal noise and extreme noise, or minimal gain and maximal gain. So we come up with a method of over-parameterizing our network, in which we partition the range of noise levels into n subranges. This over-parameterizes the original network, since there's now four sub-networks trained individually for each subrange of the problem space. And while this increases the number of parameters of our network fourfold in our case, it still only consumes 239 kilobytes, which is still within the SRAM size of a typical CNN accelerator, which is usually in megabytes. This means that although the parameter count is increased, there still is no DRAM spill caused by the increase in parameters, which means that there is negligible impact on the runtime due to this increase in parameters. The noise subrange model array leads to a very clear improvement in the traditional PSNR and SSIM metrics, and we've also visually confirmed that it yields a better detail thanks to the overparameterization. We evaluate our method on a public benchmark, the Darmstadt noise evaluation, and we achieve very comparable metrics to prior state-of-the-art that is not applicable to mobile devices, such as Cycle ISP and unprocessing images for learned raw denoising. So our network achieves comparable results to Cycle ISP while using 250 times fewer MACs. For a fair comparison, we also scale down the prior state-of-the-art such that the gigamax per megapixel is the same as our network or slightly higher, and they are scaled down by trivial means such as channel reduction. As you can see, when the compute is similar, our network is much better in these traditional metrics, and although the parameter count of Cycle ISP Lite is lower than our network, as mentioned before, this is a trivial difference because both networks will fit within the typical SRAM size of a CNN accelerator. This is the summary of our improvements, including the effect of the feature align layer, the effect of the noise subrange model array, and then the effect of the feature matching loss from right to left.